Okay, let's start off discussion of expected value with a brief review of what we did in class last time. Here we see this is the true story about the theater performance that I attended, where the entry fee was essentially 3 times the number you rolled on a die. Except if you rolled a 1, you got in free. And remember, we did the simulation in Excel. Let's see if I can show you that here. Remember, we drew the graph, and if we well, yeah, yeah, there's a different roll. Remember, we rolled this different times, and we saw that it looked like, remember, the x-axis here going across is the number of customers, and we're adding more and more customers as we go out on the graph, and this is the average fee collected, and it looked like it was trending around 10. And so what we did was showed the expected value approach. That was A, and then the expected value approach of this is what I'd like to just quickly review. So I'm going to go to a new tab here, and what I have is a table that I went ahead and made in Smart Notebook software. And then this table idea is like the general approach we're going to think about expected value. And again, expected value is what we think of as that long-term average if you repeated the experiment many, many times, or another way to think about it is call it the theoretical average, the average you should expect to get. So the way we do that is first we have to do is just think about all the possible outcomes. And here when we roll the die, we had the 1, 2, 3, 4, 5, 6 were the possible outcomes. But in this case, we're trying to find the expected value of the fee, so we actually have to translate those die outcomes into the fee outcomes in order to do the expected value. So all we're really doing here is multiplying by 3, except for this first row, it's 0 because we get in free. So here it's 6, 9, 12, 15, and 18. So essentially all we want to do is weight each outcome by its probability of occurrence and then add those things up. So in order to do that, we initially need to get the probability of outcomes. This particular problem is pretty straightforward because all these outcomes here are just 1/6 probability, because the die we're assuming is fair, and all are going to have different, or they're all going to have the same chance of occurring. You'll see in other problems that often this probability will be different for the various outcomes. And then to get the full expected value, we just multiply. This 0 occurs 1/6 of the time, so we do 0 times that 1/6 to get 0 here. This $6 outcome occurs 1/6 of the time, so we're going to multiply that to get $1. This one is the $1.50. And I've just gone ahead and completed that table to fill in what we had before, and then to get the full expected value, these were just the outcomes weighted by the probabilities, and so then we need to add these up. I guess the first thing you should always check is that in order to get a full expected value, the probability of all your outcomes needs to add to 1 to make sure everything's going to happen. And in this case, we see that 1/6 added 6 times gives us 1. And here, when we add this together, not surprisingly, we get the answer of 10. And so that's the expected value, and that would be the expected value approach to figuring out that long-term average per revenue per customer would be $10 in the theater example. So this question C then is just using that information. It says if we wanted to charge a single price for everyone, at what level should we set the price to feel like we're going to break even versus the roll of die arrangement? Well, we're never going to truly break even, because we saw when we looked at those averages that it never exactly equaled 10. But the idea is for a fair price, we would essentially, if we were going to scrap the roll of die arrangement and we wanted to make the same amount of money on average, we would just charge $10 per person as a fixed fee and forget about the random outcome. And that would be essentially break even, because with the old approach, we were expecting to make $10 per person, and if we did it for long enough and had enough shows, that's what we would make. But if we didn't like that volatility, we would go ahead and just break even versus 10. And that's often what this expected value is used for, is to figure out what this break even kind of fixed price is. So you can trade off uncertainty for something fixed. Like, that happens in insurance all the time. You have the uncertainty of accidents. How much are you going to charge to break even, so that you protect people against whatever event they're going to have, like a car accident. And so that's often when you want to figure out the break-even price, all you're really looking for there is expected value. So now for section D here, question D, we're just saying let's change the game. The CFO wanted to change the ticket price to be the number on the die squared, but rolling 1 would still get you in free. And let's take a look at how the expected value of this arrangement would compare to the original. I'm going to go ahead and complete that and then just show you the answer, and we'll talk through it quickly. Okay, here's the answer for then part D. I went ahead and took the old table that we had, and I've added a red column in here, which is essentially the new outcome. So we're still rolling the die 1 through 6. Then in the fee outcomes, I've added a red column, which would be the die squared, except you still get in free with 1. So in that case, we still have a 0 here, and then this column is just filled in with the die squared. 2 squared, 3 squared, 4 squared, 5 squared, 6 squared. Those probabilities remain unchanged. And the idea of expected value is, again, just to multiply the outcome times the probability, and that's what I've done over here in this column out to the right. This column out to the right then is fee outcome times the probability, and I've just kept them as fractions because it makes them easier to add later. So this one is just 4/6, which is the 4 times 1/6. 9 times 1/6 is 9/6. 16 times 1/6 is 16/6, etc. And that would be the contribution to expected value. And then to get the full expected value, I just need to add that column of numbers up. And down here we see that's just you add the numerators here, 4 through 30, or the 4, 9, 16, 25, etc. Do that, you get 90 over 6 and 15. So if we did this thing long term, on average, we would expect to make $15 per person in terms of what we collect versus the 10 previously. And so the question for that last one then is we expect a 50% increase.